Okay. So here is kind of the, not kind of, here is the fundamental theorem of calculus. And all it's saying, which she said in class many times, is that if you take the derivative of the antiderivative, you get back the function you started with. And we'll definitely use some examples of this to kind of show how it works. And then I will also point out there's some alternate versions that are slightly more complicated to account for when either one of your limits of integration are more complicated than just x. So if I have a g of x, so here's how I really think of it when I'm doing this. When I'm trying to find the derivative of this, I'm just like, oh, I'm just going to plug in x for t, and I get f of x. Here, instead of plugging in x for t, I'm going to plug in g of x for t, but then because of the chain rule, we have to multiply by g prime of x. So we get f of g of x times g prime of x. And the same deal here, except when we have x's in the top and in the bottom, you have to do then the top one, plug it in, multiply by the derivative, minus the bottom one, plug it in, multiply by the derivative. But let's do some actual examples and not just look at like things like this. Yeah, and then I wrote the other part too. Second part of the fundamental theorem of calculus, the evaluation theorem, it's also called. If you integrate from a to b of f of x, it's just the antiderivative evaluated at b minus the antiderivative evaluated at a. Almost everybody got this right on the quiz I gave who took it. I think one or two people did accidentally switch the order. Just remember, it's always the top one first minus the bottom one second. And then I will frequently, because it's convenient, write it like this, where we write the antiderivative and then this vertical line to mean it's evaluated between a and b, where again we plug in b first and a second. Okay, so let's do some actual real life examples. Yeah, erasers would be good. And I'm gonna hit a lot of the same points she did today because there's a lot of the same points to be made. The first one is we can actually find the antiderivative. So if I want to find, say, the derivative of the integral from 2 to x, let's pick something not terrible, like 4t cubed dt. So I want to be very specific. The variables here have to be different than the variable up here. This doesn't ever work if you have x's here and x's here. So that's why we have different letters, because we just can't do it if it's weird to have an x. It's wrong to have an x or an x here. So the short answer to this question is you take the derivative of the antiderivative of a thing, you get the thing, and that's it. But I imagine you guys would like to see a little more information. So what's really happening here? Well, we can integrate this. We know how to find the area under a curve, right? That's actually the second part, right? We're actually going to use this part of the fundamental theorem of calculus to say, okay, I'm going to find the area under this curve by finding the antiderivative of little f, and then plugging in the top minus plugging in the bottom. So here's how I'm going to write that. So first, I'm still going to take the derivative at some point. So the antiderivative of 4t cubed is 4t to the fourth over 4, which is just t to the fourth. And then evaluated, right, that's what my vertical line is for, between 2 and x. Now I'm going to plug in the limits of integration. It's always the top one first, the bottom one second. So I'm going to have the derivative of, so plug in the x minus plug in the 2. And now we're going to take the derivative. Okay, what's the derivative of x to the fourth? All right, I do want an answer for the next one. What's the derivative of 2 to the fourth?
0.
Right. And whenever it's a constant to whatever, right, sine of 2 to the fourth, natural, right, as long as this doesn't have any variables in it, we know the derivative is going to be 0. So we get 4x cubed. Something to be aware of here, right, is that the whole point of the fundamental theorem of calculus is that you don't have to do all this work. Right? You can do it all to see what's happening, but if someone gives you this question on a test, they don't expect you to do all this. They expect you to be like, oh yeah, I know that when I take the derivative of the thing, I get the thing. And that's kind of it. So don't definitely I oftentimes in a homework, there'll be like one problem where they're like, do it the short way and do it the long way. See that they're the same. But then most of the time, they just like do it the short way. So I'm going to, as she was pointing out, this is especially important because some things are really hard or impossible to anti-differentiate. For example, if I want to find, say, I'm going to try and use some different letters too, just to kind of change it up. So if, yeah, she did this. If f of theta is equal to, I don't know, the integral from 3 to theta of, I'm good. Okay, of sine of x squared dx. I want to find f prime of theta. Well, it's the same deal. The difference, not really a difference here, but something to be aware of here is that unlike the previous problem, we were totally capable of actually anti-differentiating 4t cubed and getting t to the fourth. We, and by we I mean the entire world, cannot anti-differentiate sine of x squared. It is a function that cannot be anti-differentiated. Fortunately, we don't need to anti-differentiate it. We can apply the fundamental theorem and say, oh, well, if the function is equal to this integral, then the derivative of this integral is just the stuff inside. Except it's now sine of theta squared. And that's it. There's nothing else. It does get more complicated. If I want to say, if y is equal to, say, the integral from, let's do this. So I want to go first, sure. From 1 to, x cubed of t over 1 plus t squared dt. This is something we will be able to integrate later. For which one, Emily? For this one? Both. So this one, no. There is literally no way to integrate this. So there are a class of functions. Here's another one, the integral of e to the x squared, where these functions actually don't have an antiderivative. Really, what we say is there isn't an elementary function that's antiderivative. There is a complicated way of writing the antiderivative that's literally just like writing down the integral and saying, there's the antiderivative. But yeah, this function and this function actually cannot be antidifferentiated. This one certainly can. This one you could do with a u substitution for sure. And we'll probably do it, probably not today, probably maybe Friday. But again, if I'm trying to find dy dx, well, so actually I will show you the antiderivative of this and we'll kind of talk about it. But the short way to do this would be the following. The short way would be, okay, I'm plugging in x cubed wherever I see a t. So it's going to be x cubed over 1 plus x cubed squared times the derivative of x cubed, which is 3x squared. Let me show you guys how we could do this one the long way. And part of that's going to involve me just telling you one thing. So I'm going to tell you that the antiderivative of t over 1 plus t squared is equal to 1/2 the natural log of 1 plus t squared. Let's see if James is really right. So let's check. How do you check if something is an antiderivative? You take its derivative. So if I take the derivative of this, the derivative of 1/2 of natural log of 1 plus t squared, well, it's going to be 1/2 times the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative of the stuff is 2t. A 2 cancels, and then I can write this as t over 1 plus t squared. So it is true that the antiderivative of t over 1 plus t squared is 1/2 natural log of 1 plus t squared, because the derivative of 1/2 natural log of 1 plus t squared is equal to t over 1 plus t squared. Okay, so now we're going to try doing this one the long way. I want to erase that, but also not. So yeah, I'll leave my answer down here. I see myself a little more room. So y is equal to the integral from 1 to x cubed of t over 1 plus t squared dt. We're going to evaluate this. So again, we know the antiderivative of t over 1 plus t squared is this. So we're going to get 1/2 natural log of 1 plus t squared between 1 and x cubed. Now I'm going to plug in. I'm going to get 1/2 the natural log of 1 plus x cubed squared minus 1/2 the natural log of 1 plus 1 squared. And now let's take the derivative of that. So this is what y is equal to. Now I want to find y prime, which is another way of saying dy dx. So I'm going to take the derivative of this part. All right, so let's be careful. The derivative of this, the 1/2 is going to hang out. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. But the derivative of x cubed squared, I'm going to do it the chain rule way, even though you could just say it's x to the 6 and the derivative is 6x to the 5th. The derivative of x cubed squared is 2 times my stuff to the first power times the derivative of the stuff. But look, that's exactly this. The 2's cancel, and you get the x cubed to the first. I'm going to put that on top, times the 3x squared. So whenever you have this, when you're taking the derivative of an integral, and one of your limits of integration is something that's more complicated than just x, you do have to use the chain rule and multiply by its derivative. You guys want to try? It should be relatively fast. So I want you guys to try finding the derivative of the integral from 2 to x squared of t over sine, that's not quite, sorry. Let's do sine of t over t plus 1 dt. I'm going to give you guys a minute. Of course, I don't have a stopwatch. Okay, 10 seconds left. That's time. I don't expect anyone to type their answer in the chat because it's a lot of typing. But the idea here is that we're going to get, I'm going to plug in this x squared wherever I see a t. So I'm going to have sine of x squared times x squared, sorry, not times, over x squared plus 1. And then what do we have to multiply that by?
2x.
Times the x.
Awesome. Yes, exactly. And that's it. And then the only other kind of, well, not the other thing that comes up sometimes is sometimes you have things are in the lower limit, right? So if I wanted to find, I don't know, like the derivative of the integral from r to the, let's make it more interesting. Let's pick something fun, like sine of r to -6 of, oh, yeah, or something I should say. I was going to make it a function. Let's just make it fun and juicy, like t to the 4th equals 9. So one thing she did say, which I haven't been doing, and you can usually not worry about, is your function, your thing you're integrating does have to be defined on the interval here. You shouldn't worry too much about it. Like if she wants you to look for that, you definitely should look for that. But it's usually like a very minor thing you look for. It does become more important when we start talking about improper intervals, which is a later chapter. So we'll come back to that. But for the most part now, you shouldn't be sweating if like yeah, I know this is undefined at t equals -1. It's probably not an issue. On this one, so we're going to plug in sine of r now, but since it's in the denominator, we have to slap on a negative sign. So negative, plug in sine for t, so it's sine of r to the 4th plus 9 times, now I have to think about this for a second. No, yeah, that's right, yeah, times cosine of r. I was a little unsure if all of it was times cosine or just the sine part was times cosine. I'm fairly certain this is right, but let's check. Right, we can check this. So we're actually gonna do this one the long way as well, just to kind of see. So if we anti-differentiate this, so this is going to equal the derivative still, right? I'm still leaving this symbol here to tell me that I need to eventually take the derivative. I'm going to anti-differentiate this. I'm going to get t to the 5th over 5 plus 9t evaluated from sine of r to -6. And then we're going to plug in limits of integration, always the top one first, bottom one second. So it's going to be the derivative of, we know it's not really going to matter when we plug in -6, right? We're going to get -6 to the 5th over 5 plus 9 times -6. Right, but the derivative, that's all going to be 0. Minus, then I'm going to plug in sine. So I'm going to have sine of r to the 5th over 5 plus 9 times sine of r. Okay, and now of course I'm running out of room. I think I can squeeze this in here, but it's going to be tight. So the derivative is that's going to be 0. Derivative that's going to be 0. The derivative of something to the 5th power. So here's where we have to use our chain rule skills. This is, what is this process called? I mean, we're using the fundamental theorem of calculus. I would say that this is really the, so I would say here we use the first part of the fundamental theorem of calculus. She said you don't need to know which part. That's perfectly fine. Here we're just actually doing the long way. And so I would call this process the process of first anti-differentiating and plugging in and then taking the derivative. It doesn't have a good name. It's just we're doing all the work that we can. That's kind of what's happening here. So the derivative of -6 to the 5th over 5 is 0, right? It's a constant. The derivative of -54 is 0. And then the derivative of something to the 5th power that is a function, right? It's sine of r. The derivative of something to the 5th is 5 times your something to the 4th times the derivative of your something. which is cosine of r. And then we still have that 5 in the denominator. I know it's getting very, very messy down here. I'm sorry for that. And then finally, the derivative of sine of r is going to be cosine of r. And I'm not going to write any more down here because I can't fit it in. But look, so I will point, I made a small mistake. It's not a huge mistake, but it is a small mistake. I should have had parentheses around all of this so that I'm subtracting both of these. So I really should have parentheses around all of that. And now look, the 5's cancel. And look what I've got. I've got negative sine to the 4th plus 9, and then all times cosine. You could factor, you could factor the cosine. So this is the same as that, even though it looks slightly different. So questions about any of this first part of the fundamental theorem of calculus? We'll do a couple more, but I just want to stop, pause for a second, ask this if you have any questions. Okay. You're welcome to ask questions anytime, obviously. So how about a couple more, like the derivative of the integral from natural log of x to e to the x of the square root of 1 plus t squared dt. So here we see, well, yeah, so kind of both, Emma, right? So we get a negative sign here because it's in the bottom, but that's all, and the reason it being in the bottom leads to a negative sign is that when we do the antiderivative and then plug in the limits of integration, we always plug in the top one first and then subtract and plug in the bottom one second. And so then that's why we're getting this negative sign, because we know that if we were to do this the long way, we would end up doing the top one minus the bottom one. So hopefully that kind of clarifies the question. Yeah. But you know, I feel like, so you know what, I made a tiny error in this part too. So it really should be, and I'm sorry for this, it really should be minus all of that. Sorry about that. That is a mistake I made for sure. Right? So when it's the bottom one, it's a minus everything, and then you plug in sine, and then multiply by the derivative sign, just cosine. Same deal here, right? It's minus sine to the 4th times cosine plus 9 times cosine. That's what I have here, right? Minus sine to the 4th times cosine, and then plus, which becomes a minus, and you distribute 9 times cosine. Oh, okay. Kind of a funky example. So let's look at this one. Same idea. We're taking the derivative of the integral of this, so we know we're just throwing these things in for t. So here we're going to get, so I'm going to plug in e to the x, and the square root of 1 plus e to the x squared. What do I have to multiply by? I don't think I need it. Oh, I see. I see why you would guess 2 e to the x, because I've got an e to the x squared, but I'm not plugging in e to the x squared. I'm plugging in just e to the x. And so I only have to multiply by the derivative of that thing up there, which is going to be an e to the x. Yeah. And then same kind of idea for this one. I'm going to plug that in. I'm going to get the square root of 1 plus the natural log of x squared. And then what am I going to multiply by? Well, what's the derivative? Exactly. And one thing to be aware of, this doesn't simplify, right? This 2 doesn't come down because it's not the natural log of x squared. It's the natural log of x quantity squared. So just something to be aware of. Here, if you wanted to, you could rewrite this part here as e to the 2x. But I don't think that's really the point, right? Like I would just leave it unsimplified unless someone said it had to be more work. Okay, let's do, let's I feel like we've done enough of these, unless you guys really want some more. Let's kind of go the other way to the other side of the fundamental theorem calculus and talk about evaluating things. Because, so to be really kind of straightforward and honest about this, we spend like a minute using this, and then we really, this first part, although it is fundamental and a lot of other things we're going to see are based on this working the way it does, we really don't do a whole lot of this. We don't do a whole lot of taking derivatives of integrals. We really spend more time finding what are called definite integrals. The integrals where you have numbers as your upper and lower limits of integration. So let's kind of look at that. Yeah. I'm gonna ask kind of a silly question first. What's the derivative of the integral from 1 to 9 x minus 1 over the square root of x? And I will give you 5 seconds to type your answer, because you should be able to see what the answer is in 5 seconds. Okay, what's everybody's answer?
Zero.
0. Sorry, I didn't hear you there, Chang. It's okay.
Never mind, it wasn't 0 anyways.
All right. So this is the same sort of question as before, but the difference here is that if someone asks you for them both to be numbers, oh, well, so first of all, I did something wrong. Did I do something wrong? You could argue I kind of did. I probably should use different variables, right? I probably should have actually used t's here, because that's what we're used to kind of doing. But here's the thing. This thing in the brackets here, if you find this, right, if you do the antiderivative, then plug in your limits of integration, since they're both just numbers and not x's, when you find this thing in the brackets, it's just going to be a number. And then the derivative of a constant is just 0. So someone might try to trick you like this sometime, but just know that, like, the derivative of, if these are both constants, it has to be 0. And here's why. We're going to actually calculate what's in there. So if I want to calculate the integral from 1 to 9 of t minus 1 over the square root of t, typically when we have fractions and we want to anti-differentiate, so I should also just clarify, we're going to use the words anti-differentiate and integrate pretty much interchangeably, because they're not exactly the same thing, but they're both part of the same process. Right? When you're integrating, you're trying to find the net area of the curve, or lots of other interpretations, and we use the antiderivative to find what the integral is. So sometimes we say we integrate, sometimes we differentiate. Get used to thinking of them as being find the antiderivative and then do whatever. And so to anti-differentiate or integrate a quotient like this, we typically try to divide each part by the denominator and simplify it. So I'm going to write this as, I'm going to write this as t over the square root of t minus 1 over the square root of t. And then I think she did an example with a cube root in class. It's always going to be in your interest to write powers of your thing as, well, not as roots, but as powers, and as powers in the numerator. So I'm going to write this as the integral from 1 to 9. T divided by the square root of t is the square root of t, which is t to the 1/2. And 1 divided by the square root of t is 1 over t to the 1/2. But I don't want to write it that way because it's harder to anti-differentiate. What I want to do is I want to write this as t to the negative 1/2. Dt, because if they're both written as just t to a power, we can use the anti-power rule. So this is going to be, so the antiderivative of t to the 1/2 is t to the 3 halves, right? We add 1 to the power and then divide by the new power. Minus, same deal here. Negative 1/2 plus 1 is positive 1/2 divided by the new power. And then we're evaluating from 1 to 9. Before we evaluate, I would simplify this expression a little bit. I would write this as 2/3 t to the 3 halves minus 2 t to the 1/2 from 1 to 9. And of course, we're plugging in the 9 first. So we're going to get 2/3 times 9 to the 3 halves minus 2 times 9 to the 1/2 minus. So when you're plugging in 1 to a power, you just get 1. So 2/3 times 1 to the 3 halves is just, well, I'm going to write it down, but it's just 2/3. So you get 2/3 times 1 to the 3 halves minus 2 times 1 to the 1/2. And I should simplify this even though I'm kind of out of room. So let's go up here. So 9 to the 3 halves is the square root of 9, which is 3, cubed, which is 27. So this is going to be 2/3 times 27 minus 2 times the square root of 9 is 2 times 3. And then minus 2/3 times 1 is 2/3. And minus and minus is plus 2 times 1 is plus 2. And then I can simplify this further. 2/3 of 27 is 18. 18 minus 6 minus 2/3 plus 2. So that's going to be, let's see, 18 minus 6 is 12. 12 plus 2 is 20. Wow, 12 plus 2 is not 20. 12 plus 2 is 14. And so I get 14 minus 2/3. And if you get the common denominator, it's going to be 42/3 minus 2/3 is 40/3. That's the area. That's that. Well, I mean, it's the net positive area. But what I want to point out again is, right, so this integral in the brackets is equal to 40/3. What's the derivative of 40/3? 0. So kind of neat. Kind of not super exciting. Yeah. With another example. Let's look at the integral of, what have we got here? Yeah, sure. Integral from 0 to 2 of x times 1 minus x1 squared. Soon, probably next class, we'll learn how to do a u substitution. But for now, we don't have that, so we're just going to multiply it out. So I would multiply this out as x times, so this multiplies out as 1 minus 2x plus x squared. And then I'm going to distribute. So we do have to distribute the x, right? And then I should make it really, really clear. If you're trying to integrate a product of things, right? If you want to find the integral of f of x times g of x, it is not equal to the antiderivative of f times the antiderivative of g. There is no nice product rule for integrals. There is kind of a product rule for integrals, which we'll talk about later, but it's definitely not this. So what I'm trying to say is I can't just do the antiderivative of this times the antiderivative of this. I have to multiply it out and simplify the integrand, stuff inside the integral, before I can then antidifferentiate. This is going to equal the integral from 0 to 2. So if I distribute the x, I'm going to get x minus 2x squared plus x. And then we can anti-differentiate using the anti-power rule. So I'm just adding 1 to the power, dividing by the new power. So this is x to the 1. So I get x to the squared, x to the second over 2. So minus 2x to the 2 plus 1 is 3 over 3. Plus x to the 3 plus 1 is 4 over 4. From 0 to 2. And then we plug in. We get, let's see, I get 2. So it's good to get in the practice of trying to simplify as you go. So I'm going to plug in 2 But I know that 2 squared over 2 is just 2, right? It's 4 over 2. So I get 2. Minus, now this one's next in combination. So 2 cubed is 8, 2 times 8 is 16, so I get minus 16 over 3, plus 2 to the 4th is 16, 16 divided by 4 is 4. Minus, when I plug in 0, in this case, everything is 0. 0 squared is 0, 0 cubed is 0, 0 to the 4th is 0. But I want to, in fact, I'll do another example just a minute here to make sure everyone's super on board with this. You don't always get 0 when you plug in 0. You do if it's x to a power, but you don't if it's other types of functions sometimes. So just be aware, 0 doesn't always give you 0 back. So that's going to be 2 plus 4 is 6 minus 16 thirds. So 6 is 18 thirds minus 16 thirds. So 2 thirds. Yeah. So a lot of this gets to be kind of monotonous, maybe. I don't know. It's the same thing a lot. It is definitely something you want to practice because it does take practice to be good and efficient at doing it. I know. So let me take a quick gander at you guys' homework for this week. Is there anything on there that looks kind of crazy? No, not really. But she is asking you about indefinite rules as well. Okay, cool. Yeah, all right. So let me do one more definite one, and then we'll talk about. Well, in fact, actually, let's do that. So let's do the integral. Yeah, we'll do 2 different ones. So first problem, I want to do the integral of. Sure. Like 2x plus sine of x minus secant of x tangent of x. I want to make a very, very, very important distinction. Definite intervals. When you have upper and lower limits that are both constants. A definite integral just represents some sort of net area. When you find a definite integral, your answer should always be a number. It might not be a very nice number, right? It might be pi or the square root of 2 or some wacky like e cubed plus 7, but all those are real numbers that don't have any variables in them. On the other hand, this expression here does not have any limits of integration. This is an indefinite integral. So this is an indefinite integral, also known as find the antiderivative. So instead of going through the whole kind of rigmarole of saying, here's a function, find its antiderivative, we're going to use the integral symbol without limits of integration to mean antidifferentiate, because this symbol is already so associated with the process of antidifferentiation, right? To find the definite integral, you do the antiderivative and you plug in the things. So the indefinite integral, you're just doing the antiderivative and you're not plugging in the things. So let's see what we get. Yeah. So the integral, the indefinite integral of 2x plus sine of x minus secant x tangent x dx. So one of the rules of integration is that things that are added subtracted together, right, you can kind of see it separately. So this is the integral of 2x plus the integral of sine x minus the integral of secant x tangent x. We're not going to write out 3 integrals, but that's how we're going to think of it. So the antiderivative of 2x is x squared. The antiderivative of sine of x is negative or positive cosine?
Negative.
And the antiderivative of secant x tangent x?
Minus secant x.
Cool, yeah, good stuff. And then since it's indefinite, we slap on a plus c. So when you're finding the antiderivative, you need the plus c. When you're finding the definite integral, when you have limits of integration, you don't need the plus c because the plus c cancel out. So now, if I said I want to find the integral from what's going to be fun here? Yeah, 0 to pi over 3 of the same thing, 2x plus sine x minus secant x tangent x. Actually, this kind of speaks to another point I just want to make real quick. Sometimes you're going to be given a definite integral, but the anti-differentiation process is going to be very complicated, and it might make sense to, even though you're finding the definite integral, do the indefinite integral first, just so you don't have to carry all this kind of extra baggage with you when you're doing the anti-differentiation. And then at the end, you'll be like, oh, okay, I know the antiderivative is this, so then the definite integral is this, x squared minus cosine of x minus secant of x, evaluated between 0 and pi. I know it doesn't look like anything different here, but eventually we're going to see other ways of anti-differentiating that are more lengthy, like use substitution. So here I'm going to plug in, I'm going to get pi over 3 squared minus cosine of pi over 3 minus secant of pi over 3. And I'm going to plug in 0. And here's kind of the point I was trying to make before about when you plug in 0 here, not everything's going to be 0. I'm going to get 0 squared minus cosine of 0 minus secant of 0. Okay, what is everything? Well, pi over 3 squared is just pi squared over 9. Cosine of pi over 3 is 1/2. Secant of pi over 3 is the reciprocal of that, right? Secant is 1 over cosine, so secant is 1 over 1/2, which is 2. And then minus, in fact, let's just distribute the minus sign. So minus of minus is plus cosine of 0, which is 1. And minus of minus is plus secant of 0, which is also 1. So notably, right, these things are not 0. They don't just go away. So be aware of that. And I can't say this enough because I've seen so many people over the years say, oh, it's 0, everything's 0, we're done, right? Just be careful. Right? When you're plugging in 0, actually check and see, are things actually 0? Or do I get something like cosine of 0, which is equal to 1? Okay. So then the -2 here and the 1 and the 1 here actually cancel out. And so I would probably just have an answer as pi squared over 9 minus 1/2. You could get a common denominator if you really wanted to and write it as 2 pi squared over 18 minus 9 over 18. But I don't think you can do that. Okay. So we got 5 minutes. Let me kind of, yeah. I think it's worth, no, let's just do a couple more. No, I think it is worth starting to think about a substitution problem. Oh, we had that too, though. Sure. Yeah, so maybe we'll come back to those next Friday. Okay, so let's look at this one problem. So I want to find the antiderivative, also known as the indefinite integral, of 5x to the 4th times x to the 5th plus 1. Yes, you could totally multiply this out. And actually what we're going to do, we're going to multiply it out. So one way we're going to do this is we're going to say, okay, I'm going to multiply it out. 5x to the 4th times x to the 5th is 5x to the 9th. 5x to the 4th times 1 is 5x to the 4th. And now we're going to use the anti-power rule. I'm going to get, 5x to the 10th. Sorry, this is like, I should take the screenshot of all the names before I forget. Yeah, I'll do that easier later. So the antiderivative here is 5x to the 10th over 10. And here it's 5x to the 5th over 5 plus c. And we could probably simplify this. It's what? X to the, someone wrote something wrong over there. That's fine. It's x to the 10th over 2 plus x to the 5th plus. And now we're going to do this a different way. And this is where we're definitely headed towards probably Friday, maybe next week. So another thing we can use is what's called a U substitution. And we'll get into more about how to choose what U is. But in this case, we're going to choose U to be x to the 5th plus 1. Usually you're trying to pick a U whose derivative is also in the integral. Well, that's a great choice because the derivative of x to the 5th plus 1 is 5x to the 4th, and that is in the integral. So the derivative here, du dx, is equal to 5x to the 4th. There's a couple of ways people like to do this. I'm going to show you two ways real quick. So one way to do this is we're going to start changing all of the variables from x's to u's. So I'm going to rewrite the integral of 5x to the 4th times x to the 5th plus 1 dx. Here's how some people like to do it, which is not my favorite, but this works fine. This, so 5x to the 4th is du dx, and x to the 5th plus 1 is u. So then I can write this as the integral of du dx times u times dx. And then the dx's can cancel. So I can write this as the integral of u du. Not my favorite way of getting there, but it works fine. The other way of getting there, to have room on the same board. Let me finish this off, and then I'll show you the other way. So then we can anti-differentiate this. The antiderivative of u to the first is u squared over 2 plus c. And then we have to plug back in what u is equal to. That's x to the 5th plus 1 squared over 2 plus c. So now the question, is this the same as this? Well, let's check. X to the 5th plus 1 squared over 2 plus c. If I square this out, it's x to the 10th plus 2x to the 5th plus 1 over 2 plus c. If I don't write them each divided by 2, it's x to the 10th over 2 plus 2x to the 5th over 2 plus 1/2 plus c. So let me ask you guys, are those the same? Yes or no?
Yes, they're the same.
And I would also take an answer of no. You could also say no, they're not the same. Both of you would be right. The real answer is they're the same enough. They differ, but they only differ by a constant. And as we've seen before, antiderivatives are allowed to differ by constants. You could also say that this 1/2 as a constant here is equal to the constant there, and that would be fine as well. But yeah, they're the same. So this process of U substitution allows us to integrate this thing. The way I should just point out, I know we're over time, but I'll just tell you guys, the way I typically imagine this, instead of calling this du dx, what I usually do is I like to mess with that. So I like say, oh, du is equal to 5x to the 4th times dx. And then I can rewrite my integral of 5x to the 4th times x to the 5th plus 1 dx as, well, the 5x to the 4th dx, that's just what du is equal to. And then the x to the 5th plus 1, that's just u. So I can rewrite this as the integral of u du. Slightly different process gets me to exactly the same place. So either way is fine. I'm typically going to imagine it more this way. I just did it. But if this works better for you, that is also really okay.